Good day to all. I happily welcome you all to the 20th webinar of Raman Optronics webinar series ROWS2022, organized by Raman International Optronics Society, ROWS. It's my great pleasure to introduce Dr. NAZMI SELLAMI. Dr. NAZMI SELLAMI is an associate professor and research lead in mechanical engineering and design at Edinburgh Napier University. His research is rooted in renewable energy systems with a special focus on solar energy, including the characterization and design of thermal and photovoltaic solar devices for various types of applications, especially for building integration. Dr. SELLAMI has worked on various multidisciplinary projects, including quantifying and monitoring potential ecosystem impacts of geological carbon storage and scalable solar, thermoelectric, and photovoltaics. On behalf of all the members of ROWS, I welcome you, sir, to this webinar. And I also welcome all the invited guests and participants to the webinar. A humble request to the participants. All are requested to keep their microphones muted until the end of the webinar. After the talk, time will be given for interaction with the speaker. Also, all of you, please take a note to present your screen in between. The link for providing feedback will be given at the end of the webinar. Before starting, a brief introduction about today's talk, non-conventional renewable energy systems. Every human being on this earth needs to contribute to global warming reduction. We are responsible for ensuring a sustainable and clean environment for future generations. The transition to renewable energy resources provides a solution to this worldwide problem affecting our planet. In this talk, Dr. NAZMI SELLAMI will discuss non-conventional designs of renewable energy systems. He will demonstrate the importance of these non-conventional systems, providing an opportunity for everyone to produce green energy and protect the environment. Now I kindly request Dr. NAZMI SELLAMI to start the presentation.
My name is NAZMI SELLAMI. As been introduced, I'm Associate Professor in Mechanical Engineering and Research Lead there for the group Mechanical Engineering and Design at Edinburgh Napier University, which is part of the four universities in the capital city of Scotland, the University of Edinburgh, Hereford University, and Queen Margaret University. So I'm happy today here to be with you online for this presentation on conventional renewable energy systems. My main research background falls into like design of renewable energy system, mainly solar energy system applied to building integration. And I'm going to focus on like the major problem facing the renewable energy system design. And also I'm going to show part of my research related to optical design applied to solar energy. So if we start with the beginning here, we go back to the Paris Agreement. We all talk about most of the companies from the global companies, they came together and they signed an agreement in Paris. And that agreement, it comes with a framework, and this agreement to respond to the global change, and that by keeping the global temperature below the 2 degrees, and that is in comparison 2 degrees like increase in comparison to the pre-industrial level. The pre-industrial level, we're talking about the 1850-1900 period of time. So the target for the UK is to reduce the green gas emission by at least 68%, and that is by 2030, just in 8 years. And for that is in comparison to 1990 levels, and to achieve a net zero emission, we're talking about here zero, by 2050. The European Union is slightly lower, is the reduction by 55% by 2030, same year in terms of target, and the same for the 2050. Here, what they call it, they don't call it net zero, but they call it being climate neutral. So to achieve this, most of the country, they need to come up with solution, mainly reducing the use of fossil fuel and the introduction of renewable energy. And I'm going to focus on the solar. I'm going to focus on the solar, and we're going to come up with my own analogy, the solar time, the start, the past, the present, and how the future is going to be. And I'm going to take the analogy in comparison actually to the life of a human being, the beginning of the human being from being baby until start walking and have that independency of walking and choosing the right direction. So the start was in 1950, when the company Western Electric licenses like commercial solar technology, and we have the first commercial solar cell with just 2% in comparison to now around 22% efficiency, and that solar cell had a cost of $25 per solar cell. So since then, the solar photovoltaics start evolving. I'm going to focus on the PV here, the electric generation from solar. And we had the first like commercial solar farm with 1 megawatt peak in 1982. And since then start evolving until we reached like 1 gigawatt peak of installation, 2000 capacity. But the involvement was a bit slow, so it needed like support from governments, from countries to help the adoption and deployment of PV panels. And that where started what we call the feed-in tariff, introduced in the UK, and was very generous. It's basically a system or a process of paying whoever is producing electricity from photovoltaics and feed it back to the grid. They will pay him for the amount of electricity generated and consumed at the same time, and that's why I said generated. And the past will stop in 2019, just around 3 years ago. The UK, the United Kingdom, and like many other countries as well, decided to stop and scrap the feed-in tariff scheme in 1999 to 2019. So this system is not available anymore in the UK, and we're talking about the present. The present, I mean, the solar cell that's managed to stand on its own. It doesn't need that support or subsidies from the government. And that's why now whatever the government is offering is not generous anymore. And the best rate you can get now from the UK is around 7.5 pence per kilowatt hour. And if you compare it to the current average electricity price in the UK, it's around 35 pence per kilowatt hour. It's around the fifth. Yes. So if you are selling your electricity, you are generating, you only get the fifth of what you are generating in comparison to what if you're going to consume it. So, and that when we said it's all this has got some political reason behind it, that the PV, and from one side the UK want to push the deployment of the adoption of PV panels and the generation of electricity from solar to achieve the target for the Paris Agreement. But at the same time, they just dropped the feed-in tariff for a reason, because the solar cell can stand on its own and it just cost effective. It doesn't need any help or subsidies from the government. So if you look at the UK now, they have a capacity of 14.6 gigawatt of operational PV. Most of them, they are ground mounted. I mean, they are commercial PV, and you can see from the graph the evolvement of the rooftop and commercial wasn't that big compared to the commercial one. Now the future, the solar cell, again here I'm going to compare it to the toddler. It can stand on its own and it can walk on its own without any help. And you can see here and the prediction for the UK. Even the solar is going to surpass the wind. Why I'm focusing here on the wind energy? Because Scotland has one of the greatest capacity or resources in terms of wind energy in Europe and also in the world. So, but despite that, and despite the installation of many farms or wind farms, the solar cell is going to surpass the wind, and that is for a reason, because the availability of areas in our building, and maybe the solar energy is the only renewable energy solution that can be domestic or at the residential scale. So even people owning houses or people owning small land, they can install or produce energy from renewable. So, but the problem there is a problem that can stop us and restrict that evolvement and that progress, is what we call the duck curve. So the duck curve started about is a phenomenon that was discovered around 10 years ago in California. And basically it's referring to the problem when we have a maximum solar energy or power output from solar in the noontime, 12 o'clock. As we might all know, that the most energy we can get from solar is to about noon, 12 p.m., where the sun is facing south and is at its highest. So if at that moment everyone is producing electricity, and everyone, we expect they won't be at home because we are in the middle of the day, people will be at work, people will be in the field. So it won't be that much need of electricity to be consumed locally. So all the electricity will be exported. Exported where? Exported to the grid. So the grid will face like difficulties here. So this graph we see here, why we call it the duck curve, is because of the sheep, similar to the duck. So the grid will face a lot of difficulties. And this predicted curve was predicted in 2012. And is this exactly what we reach in 2020? It's basically the amount of energy generated by solar. It will overpass or overcome the amount of energy required by the grid. In addition to that, we're going to have an increased jump between 12 p.m. and the evening. 12 p.m. maximum production minimum requirement from the residential houses. But when we reach the evening, everyone back home, is evening time. So maximum need and minimum production because we don't have sunlight anymore. And that is going to create a problem and there's a lot of pressure on the grid. So the same actually was predicted for the UK, and this is what we can see here, the prediction, how we started with basically a leveled or a net need between whatever is generated by solar. Here I emphasize on this, solar energy for electricity, and what is going to be demanded by the grid. So with that, we're going to reach a situation. Actually, the solar, yes, they can go and they can go in all direction and evolve quickly, but we have to here restrict them and we have to tie them. And this, I put this picture of this leash to the child that to restrict his movement. And to show that it's basically start happening mainly in countries when they have high resources in solar energy. I'm talking about Australia, and just was very recent, just half a year ago, in February 2020, the Western Australia roll out new rules to manage the booming rooftop solar. So to protect the grid and to ensure that they have, that the grid can support the amount of solar energy, with all new installation of PV panels on the roofs of the domestic one, they will be restricted. That means the Western Australia, they will have the power to choose either to import electricity from those panels or not. And if they don't need, so they can say, no, we are not going to buy electricity from you, and all the electricity will go to waste because those houses, they don't have access to the grid and they don't need that electricity generated. The same actually was witnessed in the UAE, Dubai. So if you want to install new PV panels in your house, you have to commit and sign that agreement. That means they will have the choice to buy electricity from you or not, according to the need from the grid. So it will be a lot of waste of energy. So, and you're going to need a solution, because that won't encourage people to install solar because we reach the saturation, and that is to do with the problem of the 12 node. So there will be, now what we need to do, we need to come up with the solutions, how we're going to do. One of them is the storage. And since we are all talking about vehicles and electric vehicles, so we talk about the vehicle to grid, which is one direction of research, very trendy now, is actually to come up with a smart system to use the batteries in our electric cars, which is increasing day after day. And the idea here is basically when we reach that maximum capacity of generation of electricity, all the electricity can be stored in the batteries of electric cars. And we suppose that all these cars will be parked somewhere, either in the car park of companies or in the house. So what we need the control, a smart control of these batteries, just to put all those energy in the cars. So with that, we're going to, from one side, encourage the use of the electric cars and make them more optimized for the users, because we're going to use those batteries that are sitting there all day without being charged or discharged. At the same time, we're going to find a problem or come up a problem for the duck curve and help to smooth it and encourage further the deployment of solar cell. And I'm trying to refer here to one project I started with. It's about optimizing vehicle to grid like integration. It's a numerical simulation, and please feel free to contact me on my email address if you would like to collaborate on this direction. Why we said the electric car? Because we started the phase out of fossil fuel vehicles, and we can see here one part of the world when they of Europe mainly, they decided to stop manufacturing and selling fossil fuel cars. Most of that will start by 2030, but by 2040, all these countries, including France, Germany, UK, the UK, so Ireland, they will stop actually manufacturing and selling new cars with fossil fuel engines, diesel and petrol. So it will be more demand and more use of electric car. So all these will come in parallel and will help each other, from one side using solar energy and the other side encouraging the use of electric car and reducing the CO2 emission. So, and I want to take this opportunity. So this one project, I worked with Robert Gordon University. He's working on the eco campers. It's one of the main touristic attraction here in Scotland, the camping and hiking and in nature. So all these camper van as well will be electric. So it's a project we work. It was funded by Innovate UK. So focusing on the integration of renewable energy on the camper van. I'm really sorry I can't share that much like results from this project because the agreement with the company, but that was the idea, and you worked on the integration of solar PV and thermal both to satisfy the need for heat for heating the camper van and cooking, and electric at the same time. So now, if we try to think and refer to the famous like cell efficiency produced and published by the famous NREL laboratory, we can see that we reach some kind of stagnation in terms of increase of efficiency for all type of solar cell. Here I'm looking at the middle part for the mainly the blue one, the crystalline silicon solar cell, which is the most used in our conventional PV panels. So there's some research, but the increase is very slow. There are some work on the emerging photovoltaic solar cell. Mainly, I'm talking about the perovskite like solar cells, but there are still some problems to solve there. But research is going there. But what I want to focus more here on is the concentrated solar cell. Is the top two plots here. As you can see, everything stopped, and that around 2014 or 15 here. And since then, only one or two laboratories, maybe one, still working on the concentrated solar cell, multi-junction solar cell. The increase in efficiency is not much, but again, the only application now maybe it will be the space application using for satellite and stuff like this. But apart from that, it's not used anymore. And if you compare it to the previous years, we can see how it was evolved quickly from 2000 to 2015 with a lot of laboratories and institute working on this research. So that direction of research is stopped for a reason, and that we were trying to explain in the next slides. We can see here on the left-hand side is basically a comparison showing the capacity of the concentrated photovoltaics, CPV, installed in megawatt. So everything started slowly in 2005, like growing in terms of installation, entered 2012, and just a huge jump from 20 to 120. There were a lot of funding available, a lot of subsidies from countries. The technology was really cost effective at that time because it was helping reducing the amount of solar cell used, the material used, and replace it by cheap material. And that helped to reduce the cost of energy produced from PV. Until the decrease or the drop of the PV material or the PV panels in 2013-14, as we can see it here on the right-hand side. And since then, it wasn't cost effective at all to use the CPV because it's going to require a tracking system, a heavier stand and the structure, and the motor and maintenance, all these kind of cost involved. So, and that's the CPV lost the battle against the conventional photovoltaics, the non-concentrated one and the non-tracking one. And since then, practically you can say there is only 1 or 2 companies still producing this, as I said, and for the only one application is the space application. It was really cost effective, and you see how things have changed. Just one research, the discovery with they made the PV panel cheaper, mainly when we started the mass production in China. So the things started dropping in terms of price, and with the increase of demand, so things start dropping. At the same time, we stopped using the concentrated photovoltaics. Now, if you go back, so the field now is only open to one type of photovoltaics, is the conventional one, the silicon solar cell, flat panels, non-concentrated one. But there is a problem. Yes, they are renewable. They produce renewable energy fed by the renewable solar radiation. But are they green or smart? The problem with the green and smart here, if you relate to the change of land use, and if you think just one utility scale of PV system range from 3.5 to 10 acres per megawatt. So just to have 1 megawatt peak of installation, we need 3.5 to 10 acres according to resources on that place. And that the fear of the land conversion that may cause significant problems to habit losses, and also to the use, those lands that used to be used for agriculture, for producing crops, foods, stuff like that. They will be changed and will be used to produce electricity, especially nowadays when the price of energy is very high. So it's very tentative and appealing for the owners to install like PV farms and start dealing with energy rather than anything else. So something has to be dealt with, otherwise it will be a major problem here that we lose our land to energy rather than agriculture. So one of the direction could be the already existing like surfaces here that we have in our habitat. We have houses, we have buildings where we live, where we commute, where we work, and we can use all those surfaces. They are ready available there, and we can use it for the production of solar energy. On the right-hand side, we have what we call applied photovoltaics. Is basically we talk about existing building, and you come up with building and you just install on top of your surfaces. It could be the roof, it could be facade, but they will be installed on top of your structure. What I want to focus on the left-hand side is BIPV, what we call the building integrated photovoltaics system. When the solar panel and the PV cells will replace the structure, it will be an active component of the envelope of the house. So these will start with the design. They have a lot of advantages here. One of them is the aesthetic, is the appearance of the house. The second one is you're going to replace the existing structure. That means you're going to be reduced of cost. And obviously, the one we talk about, they're going to use an area, a space that haven't been used It doesn't have any other application to produce electricity that can be locally used or consumed. So one of the direction, we're talking also about using the glass roof. And here is the integration of PV panels, what we call in semi-transparent installation or transparent installation, or we call it also fenestration. So this one is glass-to-glass PV panels. It's basically we just sandwich solar cells between two glass surfaces or plates, and we create that nice environment of daylight control in addition to generation of electricity. And this can be used for many large or public places, like we can see here, a stadium, could be a mall, it could be university or large public spaces. So that same applied to roofs can be applied to facades here. We can see here like a vertical facades. The left-hand side picture we see about the stairwell here, when we used the same principle, and we can actually control the transparency by increasing the gap between the solar cell. But as you can presume, by increasing the gap between the solar cell, actually we're going to reduce the electricity generated from that PV panels. On the left-hand side, we can see the view from inside. It's good. There is kind of day control, but there is a problem here. The problem faced with the solar cell when installed in vertical facade in windows is basically the obstacle, the objection of the view and the comfort of the users. These, if you have a good window, you want to enjoy the view from your window, you have to see, you want to have a good view. It could be like your garden, or trees, or anything else. But with having these, they are quite opaque, and they will disturb that comfort we have in our houses. And there where the direction started with, of research started with solutions. One of the solutions is the semi-transparent thin film or PV panels. And one of the company based in Cambridge came up, it's called Polysolar. They come up with kind of PV panels. It's based on thin film, semi-transparent, but the problem here, they had different colors. So the color here, they had orange. As you can see from inside, yes, there are some transparency level. You can see the outside, but with the change of the tune of the color of the background, which I don't think everyone will enjoy this. It's like the stormy weather. Some company, they found the use of this one, like this, the petrol station of one of the food market here, Sainsbury's. But again, their theme color was amber or orange. So they really liked it and they embraced it for their petrol station roof. But as a whole, like a residential use and windows, it didn't find that much like people wanting to install this because that problem with color. So there where I want to introduce my research, because of those problems, we tried to actually combine both. One of the direction of research which we think there's a lot of advantages, which is the concentration. And the other one is all these surfaces. Now, even the new buildings, we're trying to increase the fenestration. We're trying to increase the number of transparent PV panels. And here is one of the research we initiated is using concentrated photovoltaics in windows. So the use of concentration in windows. So there are two motivations there. One of them, we're going to reduce the opaque solar cell that is blocking the view by reducing the amount of solar cell and replace it with concentrators. As you can see here, our first prototype using transparent solar cell. The transparent concentrator, as you can see here. So all these are transparent concentrator, and they are static, so they don't need a tracker or a tracking system. So because they are transparent, so they're going to increase the transparency of our window and the view, the connection with the outside. So, and there when we came up with the design and our patent here published, is one of the shape, is called square elliptical hyperbolite, SEH. The square is for a reason. The exit aperture here, when the solar cell will sit, is a square shape to match the conventional size and shape of the solar cells. And the ellipse is why you call it, is the entry aperture, elliptical entry aperture. And that to match actually the movement of the sun from east to west. So is to capture the maximum solar radiation during the day when you are facing the right direction. So the height and the different dimension of this was optimized using what we call a ray tracing technique, and based on one fundamental known phenomena in physics, which is the total internal reflection. The total internal reflection, you might guys know more about me, more than me about this, is at a certain critical angle when the light travels from one medium to another. So is going to internally reflect rather than refract and exit to the other medium, as you can see here on the right-hand side. So we try to optimize our design to have always the sun rays when they are hitting our concentrator to have this internal reflection. So that in this way, we manage to have like totally transparent concentrator, valid, and they are good use for installation in PVs or in fenestration. So these are some of the results of our ray tracing software we used. So it's basically we follow the ray of the sun rays until we try to optimize the reflection, and here we collect the amount of rays concentrated that will be focused on our solar cells. What we can see here is a 3D distribution map showing the different concentration distribution, which is one of the things that could be improved, and one of the area of research we are working on here to see the effect of these high spots on the solar cells. Till now, we didn't find that much problem because the sun is on continuous movement, and this hot spot is moving from one place to another in the solar cell. And with that, we managed to reach a concentration from 2 to 4 times. So that means we can reduce the amount of the solar cell used 2 to 4 times and increasing the transparency by the same parameters. So all these, they've been integrated in real windows and been tested in Edinburgh in our solar test site. As you can see here, our first prototype installed in Edinburgh. And here where we integrated different optimized dimension and shapes of this concentrator by monitoring the different solar radiation parameter, the component, the diffuse, the global, and the direct. And we just managed to validate our design and the design of the third system, and we come up with these results, where we did some simulation based on the energy generation from PV panels and the optical simulation of our concentrators. As you can see, our optical efficiency can reach 45% when we have an angle of incidence of 0. You might say it's a low efficiency, yes, but again, we have the advantage here that we are using surfaces that haven't been used before, which are windows. We have increased the transparency of this window, and also we are not using any tracker. And by using the concentration, and we have a concentration of 4, so with the 50 or 45%, we can have a concentration of around 2%, covering pretty much the whole day. And here we can see the angle of incidence, and from there we can refer to the time of the day. So these are the result of our experiment. And I want to refer quickly what we did. We just referred to specialist people in architecture, and we asked them to come up with a visualization of these concentrator when they are installed in real buildings. So these are the concentration, and they can be used in many application. So wherever we have like a glass, like it could be train station, could be like here it's got the first one. The second one is the greenhouses for agriculture, or what we call the garden house for houses. So from all these we started to choose the Mall of Emirates, the famous huge mall in the UAE, in Dubai, where we have the ski slope. And there they have a huge dome in the center area. And we said, okay, we're going to cover this area with our concentrator and with the solar cell, and we're going to see how it's going to affect the view. So what you can see here, these are 100% realistic because we included all our concentrator there. And this is how it's going to look like. So as you can see, the transparency is there, the connection with the outside is there, and that is from outside. These are the gap is going to permit the daylight control. So using our here SEH concentrator, we can see the control of light to concentrate the solar cells, and we can see it's not affecting at all the view or the aesthetic of the building. And this is from inside. So the right-hand side is without cells, and the left-hand side is with solar cell and concentrator. And you're going to see how it's going to affect the daylight ambience inside the building. So here from morning to evening, when the sun is moving from east to west, moving by the south, as you can see, he's creating like a diffuse, gentle light rather than harsh light of high intensity sun rays in the Middle East. It's basically, it has the advantage of reducing the cooling load and using the solar cell to produce electricity, in addition to reduce the amount of tinted solar cell that you have to use in this kind of environment. So these are the solar cell, and this is how they look like if you use them in this kind of building. So if you look from more details, so this is from inside to outside. These are our solar cells. They give good transparency, good daylight. So in terms of absorption, so I want to focus on this figure. Sorry, let's go quickly. So we focus on a specific location here, and we, with our calculation and validated simulation we did, we can say, oops, that that area could produce around 0.5 megawatt peak. So the installation could be similar to 0.1 mega peak with just an addition of 10% of weight, which is not much in this type of structure. So this is an idea about, it's like one area of research when we use like the optical simulation here. There's a lot of improvement now on this kind of static simulator using different transparent material to improve the concentration and the transparency. I'm aware of the time. I will go quickly from there. Also, we thought about the thermal energy, which is highly required here for heating our houses. So we used, again, a static solar concentrator here, but this time with the novelty of adding absorber. So with the concentrator, you can see here where we have a reflective side, we're going to have an absorber or with a heat exchanger embedded inside to collect the thermal energy. So this is what we call PV thermal, but this one has got reflective and absorptive surfaces. So we did the simulation and optimization. Our first prototype actually was measured with our collaborators in Heritage Dubai campus. There where we can we have tested them. We are now tested it in Scotland, and also we are open with all kind of contribution with all location around the world, the globe, if someone would like also to be involved in this collaboration, testing this prototype in terms of production of thermal energy, electric energy, and also improving the design. So these are the two solar non-conventional solar energy we are working on. This is another area of research I'm working on in parallel. It's not to do in solar, but also it's non-conventional. He is talking about hydropower, not the conventional hydropower we talk about. It's hydropower to use all these kinetic energy in our pipes and our fluids flowing there, and also in rivers, is talking about conduit hydropower using kind of like a spherical shape of hydro turbine. So this is a project we start working on. And what we did here, we tried to optimize the design based on lift and drag turbine, hydro turbine. The first one here you see on the left-hand side is a lift using airfoil, and the other three is a drag turbine. And what we did here, we optimized the number of fins and the thickness for the optimum production of energy. So this is one of the CFD simulation results we used for the optimization, but also, as you can see here, also we did the experimental simulation to validate our numerical results. And what we found out in terms of density comparison, power density comparison, that the two hydro turbine studied here for conduit application have a very high, actually, I would say, power density comparable to oil and even to nuclear. They have very good power density. So they don't need that much space because we are using existing flow and pressure in our fluids that can be regenerated and used for power generation. So another one is not my research, but I was really fascinated with the idea I wanted to finish with. Is basically what you can see here, and they call it the crystal ball. A crystal ball, like to predict the future. We don't believe. I don't believe in. But again, here is the design of the aesthetic. It's basically that spherical glass ball used here to concentrate the light on a tracking system, which is compact here when you're going to have the solar cell, and that is to produce electricity. It's got high power density as well, and on top of that is quite appealing in terms of aesthetic. So I put here the link if you want to know more about this system, but it's a non-conventional one of the use of the solar energy, and to overcome the problem of the CPV that faced in the last 5 years because of the cost efficiency. So there are other directions. One of them, or the main one, could be the aesthetics and the appearance. So finally, we don't have to look far. So the solution is not down here, but is above the sky, where we have the sunlight, the free source of energy. Thank you again for your attention and for this opportunity. Here I'm sharing my email address. If you have any further question, or if you want me to send you any other resources or sources of what I have presented today, and I will be pleased to answer any question if you have any.